Great, thank you very much. It's a pleasure to have Andreea Diaconescu with us today, all the way from Toronto. It's not that much snow for you, Andreea, but we have what we can do, so please enjoy it. Andreea is an independent scientist at the Krembil Centre for Neuroinformatics and CAMH. She leads the cognitive network modeling team, and you will hear more about what cognitive network modeling is later today. She leverages her extensive expertise in computational psychiatry. She also holds an assistant professorship in the Department of Psychology, Institute for Medical Science, and the Max Planck University of Toronto Centre for Neural Science and Technology. Dr. Diaconescu's research is centered on the clinical validation of computational models of aberrant belief formation, which is pretty important for paranoia, delusions, and all the psychotic symptoms, for predicting risk of psychosis and also response to treatment in people who seek help for psychotic symptoms, particularly youth populations. Using behavioral tasks, she uses electrophysiology and also neuroimaging methods. Her contributions are very significant to the field. They have been acknowledged with numerous awards, which includes the WB Templeton Award, the Novartis Foundation Medico-Biological Research Award. Her research is currently supported by the CIHR, many project grants, which is always good to hear, NSERC, the Discovery Fund, and also the Canada Foundation for Innovation. Please join me in giving a warm welcome to Andreea today. Thank you, Andreea.
Thank you so much for a lovely introduction and for inviting me to speak at the Douglas today about cognitive network modeling and its clinical utility in psychosis. So first I want to start out by introducing, let's see if this works.
I have to click the computer.
And then it would work. Okay, turn on. Then, yeah, perfect. So to introduce the approach that we're using for understanding psychiatric symptoms and addressing mental health challenges, I want to provide you with this example, actually from internal medicine. Imagine that there is a patient that presents themselves at the clinic with jaundice or yellow skin. That is caused by excess bilirubin in the blood. Based on this observable symptom, there are at least 3 possible causes of jaundice, which include hemolytic anemias, so there could be metabolic reasons for jaundice. It could be viral due to a hepatitis virus that affects the liver functioning. Or it could also be autoimmunological that is related to dysfunction of the gallbladder. So there are a set of mechanisms that are essentially reflecting the underlying causes of this observable clear symptom of jaundice. And based on those causes and mechanisms, there's a handful of tests that one could administer to rule them out. So one could administer blood tests, ultrasound of the gallbladder, and so forth to decide on the best treatment. So this is a condition where we go from symptoms to mechanisms that reveal underlying causes to specific clinical tests. And this is very informative, obviously, for the patient because it leads to, tailored treatment and less kind of trial and error for treatment selection. Now, in psychiatry, we have the Diagnostic Statistical Manual. We have a way of classifying and categorizing symptoms, particular diagnoses. And based on these classifications, we select specific treatments. Now, often we arrive at the specific treatments without being informed by specific clinical tests, but rely on these descriptions and categorization. So we go from symptom to treatment without really differentiating the key mechanisms that lead to the specific symptoms. So what we're proposing in my lab is to use mathematical modeling as a microscope that allow us to look into the underlying or latent causes of particular symptoms that allow us to pinpoint specific mechanisms that explain symptoms, mechanisms that can be targeted by treatment. So we want to bridge the symptom level to the treatment level through uncovering key mechanisms. And what are the types of mathematical models that we use in my group? Well, these mathematical models are generative, which means that they can generate data. And one advantage of these models is that they allow us to make very specific hypotheses. So we can use the model to formalize specific hypotheses regarding these underlying mechanisms. And we can, in a way, test these hypotheses in silico through simulations. And they allow us essentially to infer on hidden neural mechanisms or neural mechanisms that we cannot measure directly through the type of non-invasive recordings that we use, but they still allow us to infer on these underlying latent causes from data, non-invasive data that we can record in patients such as EEG and fMRI. So what is cognitive network modeling? In cognitive network modeling, we try to link 3 levels of innovation. The first is the design of cognitive tasks that probe specific core symptoms in psychiatry, and tasks that are portable, so can be administered online, on tablets, or in a very controlled experimental setting. And one of the core aspects of the tasks is that they assess the underlying mechanisms that lead to specific symptoms when coupled with mathematical models or computational models of behavior. So we design the tasks with a computational model in mind. So here is a schematic of this process where we hypothesize that the agent embedded in a world is continuously making predictions about hidden states in the world and making decisions or acting in the world according to those predictions. And that internal model is constantly updated through the experience of sensory inputs from the world. Now, the true hidden states here that cause the sensory inputs that the agent is observing, those are the experimental settings that we place the agent in. Those are the cognitive tasks. So as the experimenter, we have access to this generative process. We have access to the true hidden states. That's how we design our experiments. And then based on that, we can infer on what is most interesting for us, which is the individual level parameters that govern how an agent, a participant, approximates these true hidden states and how they update their predictions about those true hidden states. And we can integrate this with neuroimaging, with electroencephalography, for example, to assess how amplitude fluctuations, trial by trial amplitude fluctuations, change as a function of learning, and learning that is guided by these particular cognitive tasks. And we can do the same with fMRI. We can look at what are the cognitive networks, what are underlying brain networks that help us explain the behavior that we can measure using those tasks. So we have two kind of research pillars in my group, and the goal is essentially to use mathematical models for early detection and prevention of severe mental health outcomes. One focus is psychosis, so trying to understand the formation of delusions in early psychosis and at-risk populations. And the second pillar is related to understanding suicidal thoughts and behaviors, how they emerge transdiagnostically in individuals with depression and psychosis. So these are our two research pillars. And I talked about the type of clinical tests that we might use in internal medicine to infer on the underlying mechanisms of jaundice, for example. In my lab, we suggest very provocatively that perhaps these clinical tests could be essentially be gamified learning tasks that become useful when combined with computational models. So, what if these gamified tasks, these very simple games that participants can respond to and interact with either in a set controlled experimental setting with EEG and fMRI, or on a tablet or on a smartphone. What if they could allow us to infer on these hidden latent causes, on these underlying mechanisms, perhaps by assessing behavior and modeling that behavior during those gamified tasks? We could use these mathematical models to track participants over time and make very specific predictions as related to treatment response. So these are some of the core tasks that we use in my lab. We call kind of jointly mind metrics, as they allow us to assess different mechanisms related to psychosis risk. So we have, of course, you might recognize the auditory mismatch negativity task, CAPIT. So this is essentially used in combination with EEG to assess an individual's sort of internal surprise signal in response to changes in statistical regularities in this context in the auditory domain. We also use another set of cognitive tasks that assess specific interpersonal processing, so in the context of social cognition, probabilistic reasoning, valence learning, and cognitive control. And we have very specific reasons for choosing these tasks based on very specific hypotheses of which mechanisms might play a role in the context of psychosis or suicidality. So this is the outline of my presentation. I'll talk about the theory and the model, in particular in the context of psychosis. Then I will showcase some of the applications that we've pursued across these very different domains of learning. And for each section, we have sort of the outlook or the future direction of how this work could be integrated in the clinic to facilitate decision-making. So I'll first start off with what kind of inspired me in the context of psychosis to look at this from this particular perspective. And I want to start off by highlighting two testimonials from patients. And as we know, psychosis is a very intrusive disorder that alters one's perception of reality. A patient might say, my senses are sharpened, sights and sounds possess a keenness that I've never experienced before. While another patient might say, I had to make sense, any sense, out of all of these uncanny coincidences, and I did it by radically changing my conception of reality. So very different types of testimonials that also highlight the complexity of psychosis and also the fact that it's not only a heterogeneous disorder, but also a disorder that progresses in stages. And each stage is marked by an increase in symptom severity, and you have positive symptoms. I'm not talking about negative symptoms here, but those are actually very important, and in many cases, they are an unmet clinical need in this context. So in order to make a diagnosis of schizophrenia, we need patients present themselves with at least 2 of these symptoms listed here for longer than 1 month, which suggests that diagnosis happens quite at a later point of this very complex progression of the disease. And even though we have a range of treatments to choose from, the challenge is the poor and reduced functioning experienced by many patients, treatment resistance, particularly for negative symptoms, but also recurring hospitalization, occupational disability. So how can we improve treatment in psychosis through this approach? And coming back to these testimonials, perhaps one way to understand is to propose a mechanism, a process for how one might arrive at those perceptions of the world or concepts about the world. And it all goes back to the Bayesian approaches, or to the Bayes rule, this idea that the function of the brain is to constantly update predictions or hypotheses about external or hidden states in the world. So this proposal that the brain is a Bayesian inference machine. And at the heart of this proposal is, of course, the fact that on the one hand, prediction errors or surprise signals that reflect the discrepancy between the input, the sensory input that a patient or an individual experiences and their model of the world, those predictions function to update one's model so that the next hypothesis, the next prediction can be more precise and allow one to adapt to a changing environment. But one aspect of this updating process has to do with precision, or how much we rely on those incoming sensory inputs or those incoming prediction errors compared to how much we rely on our predictions or our model of the world. And so a colleague of mine, Andreea Oliviana, proposed this hierarchical conceptualization of the Bayes rule, which essentially is a very generic learning model. And one can cast various reinforcement learning models like Scuola Wagner within the same framework. And the hypothesis is that the weight that we place on prediction errors is dependent on the precision. That's the same as the learning rate in a Scuola Wagner model. However, this learning rate could be broken down into a ratio of precisions that essentially assesses the degree of reliance on prediction errors, things that we experience through our sensory systems, and versus our the confidence that we have, or about our model, or that our model is correct. So in other words, we say that the belief update, how much we change our model of the world, not only depends on the prediction error, but it also depends on the sensory precision that essentially augments the impact of that prediction errors have. And of course, that can quickly become maladaptive if we change our model of the world too quickly then our model becomes very brittle. So if we move into a different environment, we're not able to, we have to relearn everything again. We're not able to generalize from one environment to the other. So the counteracting force here in the denominator is related to the belief precision or the confidence that we have in our model. And so, of course, if we're overly confident in our model, then we don't attend to what is happening in the moment. So we're not incorporating these error signals into updating our model. So we have this sort of continuous balance that we maintain. Now, this is reflected in a hierarchy. So we can think about in the context of learning and association. So what action is most rewarding? We can conceptualize it in terms of precision-weighted prediction errors, this weighting of sensory and belief precision. But if we think about it at the next level in the hierarchy, when we learn a certain association, there's a lot of evidence that in a changing environment, this association could change over time. So we're not only learning about that association, but also about its rate of change. So the same concept applies about how we learn about change and contextual change, most importantly. So the idea is that this learning process or this belief updating process travels up the hierarchy to inform our beliefs about contextual change. So if we overweigh prediction errors, then we also experience the environment as changing more quickly, requiring adaptation. And so that updates beliefs at the next level in the hierarchy. So what we can do is we can extend this computational framework to say that the agent not only makes predictions about particular associations reward in their environment that are updated through outcome prediction errors, they're also learning about the generalizability of those associations. So how stable they are, how quickly they might change. So one perfect example of that is if there's an external event that perturbs one's stable learning process, like for example, the pandemic has forced everyone to unlearn and relearn new things, led to change in our day-to-day routines. So that's essentially what this is reflected here, that our learning about rate of change or context is also governed by the same process of precision-weighted prediction error, where we have now a volatility prediction error that we can use to update our beliefs about stability and change over time. And in our lab, we hypothesized that different networks in the brain, and specifically different neuromodulatory systems, signal different aspects of this learning process. And of course, you don't need the hierarchical Gaussian filter necessarily to assess the influence of contextual change or volatility. There's many different models that take that into account. But essentially, what we're saying in my group is that we can put and pose an equation or have a specific formulation that describes the function of each neuromodulatory system and gives us a blueprint of how to assess the complex interactions across different neuromodulatory systems. And of course, this goes back to the treatments and to the underlying causes that are targeted by those treatments. How, for example, the cholinergic and the dopaminergic systems interact in the context of psychosis that can inform us why someone might respond well to risperidone, whereas someone else requires a clozapine switch, for instance. So understanding these interactions will also help us be able to understand why certain drugs are beneficial for certain patients, but also how to develop more precise or specific targeted treatments. And of course, at the same time, we're looking at this with EEG. We want to understand the interactions between the inhibitory or excitatory neuronal populations at the level of a cortical regions, at the level of a cortical column, specifically to understand the role of hyperexcitability or disinhibition in psychosis and what NMDA receptor plasticity, why this is at the center of these very detailed processes, and we can use non-invasive methods such as electroencephalography when in combination with specific neurocomputational models that describe computations at the level of the cortical column, we can address some of these competing hypotheses regarding the underlying mechanisms for specific symptoms like auditory hallucinations, delusions in early psychosis. So I want to go back to these testimonials and kind of highlight the prediction that we made regarding at-risk populations and early stages of psychosis. So we hypothesized specifically the role of precision and in this imbalance in the precision ratio. So we know from the work of Andreas Heinz, Florian Schlagenhoff, Kshitij Kapoor, aberrant salience, the aberrant salience hypothesis is hyperlearning or increased representation of reward prediction errors, outcome prediction errors. Based on this work, we hypothesized that there might be a role of sensory precision, so that at early stages of psychosis, patients are overweighing noisy prediction errors or random occurrences that might not reflect a change in the environmental context or just noisy perturbations in the environment, and don't have an impact on one's model. But in this case, by overweighing these incoming prediction errors, this model of the world becomes more uncertain and more malleable to change. Coupled with that, as related to NMDA receptor antagonism, we hypothesized that it's not only about the increased sensory prediction errors through the increased availability of dopamine in the striatum, for example, but that is coupled with overall reduction in one's confidence about their model of the world. So a reduction in the higher level belief precision that essentially acts in the same way by increasing the phasic component of the learning rate and how much one learns. So our hypothesis is that we have this imbalance between the sensory precision and the belief precision, where that leads to an overweighing of prediction errors. Of course, this is not adaptive because it leads to a lot of uncertainty. It reduces how much we can generalize our understanding of the world to different contexts. So what about delusions that tend to be very precise and very functional in some ways because they help us make sense of certain unexpected events in the world? So our hypothesis was that during delusional conviction, which is not delusional mood, but delusional conviction, perhaps these higher level precisions about the state of the world, they're actually increased in order to reduce that uncertainty about states in the world. And they are, in a sense, compensatory or adaptive, but of course also lead to very rigid, unchanging beliefs. So how does this apply at different stages of psychosis, and how can this be addressed with these different tasks? So, of course, we're big fans of the auditory mismatch negativity paradigm. It's very simple. Subjects just listen to tones that, let's say, vary in frequency while doing a visual distracting task. So, for example, here they have to predict when the cat jumps over the puddle, and so they have to pay attention to that specific visual task while listening to changes in the sounds. And we manipulate not only the association, so what is more likely, a high tone or a low tone, but we also manipulate the volatility. So when the high tone is the predictable one, when the low tone is the unpredictable one, to assess really how the brain is tracking these statistical irregularities over time. And this task allows us to assess the representation of these different quantities, these different types of prediction errors, the sensory prediction error, the volatility prediction error, and the role that these different precisions might play. And we can assess this with EEG. We can model the trial-by-trial amplitude fluctuations using this computational model of learning. We can also fit a neurocomputational model to the averaged ERPs that are constructed based on that specific individual's experience of the statistical irregularity. So instead of categorizing things as standard versus deviant, we can create conditions that reflect, let's say, high-low outcome prediction error versus high-low volatility prediction error. And our hypothesis is, of course, that the reason that we will see a reduction in the mismatch negativity or a reduction in the surprise signal that we can record with EEG, that this is related to this increased weighting of outcome prediction errors due to an imbalance between the sensory precision and the outcome precision. And that leads to, if we were to create, instead of standard deviant ERPs, we can create ERPs based on the magnitude of the prediction error at various phases of our task. We can look at those ERPs, and our hypothesis is that reduction in the difference waveform is due to an increased precision-weighted prediction error. So two members from my group have looked at that in collaboration with Michael Kiang at CAMH. We showed that increased sensory precision-weighted prediction error that we could assess with EEG was correlated with positive symptoms in positive SIPS scores in clinical high risk for psychosis individuals. Then Daniel Hauke, a PhD student in my group, took this one step further and wanted to look at what about in clinical high risk and early psychosis, do we see sort of a progression of these effects? And in this sample, this is a study we did in collaboration with Daniel Matalon. We also, the clinical high risk group had also a percentage of participants that had converted, had later converted to psychosis. So we could show essentially that this increased sensory precision weighted prediction error effect was predictive of which clinical high risk individuals converted to psychosis or not. And then when comparing it with recent onset psychosis individuals, we see a progression of this effect. So even higher precision weighted prediction error in the schizophrenia group compared to clinical high risk and then compared to controls. So we also wanted to understand the specificity of this increased precision weighted prediction error effects and positive symptoms. So we also performed a pharmacological study where we used psychotomimetics to elicit positive symptoms in healthy volunteers. So this was in collaboration with André Schmidt and Franz Vollenfeiter in Switzerland. And in this case, we looked at these precision-weighted prediction error effects under ketamine versus psilocybin. This was a placebo-controlled crossover design where participants were either given infusions, ketamine infusions versus placebo, or psilocybin capsules versus placebo. So these were two distinct groups that were randomly assigned to each kind of intervention arm. And what we found was, interestingly, an interaction between the drug and the effect of the higher level volatility precision-weighted prediction error, where while ketamine reduced the effect of the volatility precision-weighted prediction error, thereby leading to an increased uncertainty and belief precision, psilocybin augmented this effect. So we also investigated how these precision-weighted prediction error effects correlated with subjective symptoms following the psychotomimetic intervention, such as disembodiment and impaired control and cognition. And we found that the specific effect on the higher level volatility precision-weighted prediction error also predicted increased disembodiment and more impaired control and cognition. Now, what do we do with this work? So we're planning additional studies in the clinical high-risk population, specifically to see how these computational parameters can be used to predict functional outcomes. So we're not necessarily focusing on conversion to psychosis per se, but trying to predict functional outcomes such as increased severity of symptoms, but also just overall psychosocial functioning, as this is much more critical for patients. And that's a study also in collaboration with Lena and Alpen. Now, of course, in the context of psychosis, some of the more common deficits are in the social domain or impact interpersonal processes. And this was something that I was particularly interested in, specifically in persecutory delusions, persecutory ideation, in that it was common in the clinical high risk for psychosis population, but also I wanted to understand what role ambiguity and uncertainty play specifically in this context of interpersonal processes, since it is much more critical in this context, since intentions are very ambiguous and also not necessarily reflected through kind of clear social cues. They have to be inferred from someone's behavior. So, of course, to understand that, we took a step back and tried to kind of use this computational approach to understand what is it about delusions. They are resistant to change, they're present despite evidence to the contrary, and why is it that delusions about others' intentions are so robust and so difficult to dismantle, even after successful antipsychotic treatments. So things like they're all in on it, it's like the world is revolving around me, people are aware of my thoughts, people are watching, people want to harm me. And specifically, there are core symptoms that also increase risk for suicide, and it seemed like, it was very important to address this through our studies. Do you mind reconnecting it? So to do this, we designed a simple advice-taking task where that can be more easily gamified, where a participant has to infer on the hidden intentions of another person who's providing advice. So we tell the advisor is more informed about the likelihood of rewards, but is not, but has still incomplete information. So even if they provide bad advice once in a while, they can do it just due to a simple error. But at the same time, they could be incentivized to change their strategy. So bad advice can also be purposeful. So in this simple game, the player is interacting with a cheeky monkey. And this monkey, and they're in the jungle. Their goal is to explore the jungle and accrue as many rewards as possible. So you have rewards hidden in different parts of the jungle. They have to decide which way to go, left or right. And this monkey has knowledge or a map of the jungle, but the map is jumbled up. So the monkey doesn't have full knowledge of where all the rewards are, but definitely more knowledge because it has access to the map. However, you have these pirates that try to lure the monkey on their side so that they can win the treasure. So the goal of the player is to listen to the monkey, but also learn when the monkey will stray them away from the reward. And in the original setting, we had interactions with real participants and performed kind of a binary lottery version of this. But essentially that allowed us to come up with a very specific model of the learning process in this task, and also the cognitive network. So how that is represented in the brain, how that leads to specific error signals that can be measured with EEG. So we had multimodal assessment of the learning in this context. So this is what the gamified version of this looks like. So participants move into this through this jungle, and they interact with the monkey. The monkey tells them which path to choose, and they, based on the decision that they make, they see the outcome presented in terms of whether they receive the reward or whether the pirate takes it away. So what are the key features of this task? Sorry, just taking the animations next. So some of the features of this task have to do importantly with the advice, which is that the input structure that we designed is based on real interactions between participants and a very specific incentive structure, which leads to helpful advice, misleading advice, and changes in that advice validity over time. So there is intrinsic volatility to the advice itself, but also instances where even though the advisor, or in this case the monkey, intends to help, they mistakenly mislead and so forth, so that there's always a degree of uncertainty from the perspective of the player about the monkey's changing intentions. So going back to this generic hierarchical Gaussian filter model, we propose two hypotheses of what might drive aberrant learning in this context. And one hypothesis was exactly related to this increased sensory precision of incoming prediction error. So we hypothesized that we should see an enhanced phasic component of the learning rate that essentially is increased sensory precision weighted prediction error that leads to aberrant learning from the advice and leads to participants relying on the advice when it is volatile or misleading, and not when it's actually stable and helpful for accruing more reward. Now, the competing hypothesis was that, what about the higher level belief precision? We hypothesized that that would be lower. That would also lead to an increased learning from prediction errors, but not due to the learning rate at the lower level, but due to perception about the volatility of the advisor's intentions at the higher level. And when that expected volatility is high, then participants are more likely to change their beliefs more quickly in light of misleading advice or unhelpful advice. So two different mechanisms leading to the same performance differences or behavioral deficits that could be assessed in this task. And we, of course, tested this in healthy controls, and we found that the winning model was the one that was specifically looking at the phasic component of the learning rate driving the learning process in this task, and that in general, participants integrate two sources of information. That's their own perception of the reward probabilities through sampling, but also the advisor's fidelity. Now, with fMRI, we found that these two different precision-weighted prediction errors could be represented in two different parts of the brain, dopaminergic and cholinergic regions of the brain. We were able to reproduce this effect by using the same task or using a variation of the task that allow participants to infer on the probability of the reward over time. And now the next step was to apply this task in the context of psychosis. And in this study, Daniel compared clinical high risk with first episode psychosis individuals and basically found that, for some reason it doesn't work to jump the slides. We compare these two different hypotheses, and interestingly, what we found was that we could reproduce what we saw previously in healthy controls in terms of model attributions. In first episode psychosis, we see that the second model that proposes an altered perception of volatility explained the behavior better, whereas the clinical high risk for psychosis population was somewhere in the middle. So it was basically undecided model attribution. Now, if we want to look at how well this altered volatility explains behavior in the clinical groups, we see that the model can predict failures in advice taking as a function of changes in volatility. And the parameter estimates, assuming an increased perception of volatility over time, correlated with positive symptoms and also paranoid ideation in the clinical high risk and first episode populations. And we also found correlations with specific positive symptoms as well as with negative symptoms. So in particular, the kappa coupling parameter was negatively correlated with negative symptoms, which suggests that in cases where informational uncertainty is overwhelmingly high, the model becomes no longer hierarchical, so becomes basically disconnected. And in those individuals with more severe negative symptoms. And so the conclusion, we find evidence for this imbalance between the precision-weighted prediction errors, sensory precision compared to the outcome precision. Now, in the as an outlook, we are now using this gamified learning task with fMRI EEG to predict treatment response to first-line antipsychotic interventions, and hypothesizing that this increase in the or altered perception of volatility will predict who will respond to risperidone, for example, or first-line antipsychotic medication, versus who will require a switch to a medication that also has cholinergic effects. So we have some very specific hypotheses about which parameters are likely to predict treatment response and how useful they will be in predicting that. Just very briefly, the other type of task that we're using that looks at probabilistic reasoning and essentially sampling based on this FISH task. It allows us to assess jumping to conclusions or how confident someone is about the statistics and the probabilities, for example, in this case, of fish in the pond, and whether they're more likely to be sampled from pond A versus pond B. What we did in this gamified version of the task is to model this. So the hypothesis is that this jumping to conclusions bias that we see in schizophrenia spectrum disorders arises due to belief instability. So where beliefs change more quickly from one extreme to the other, essentially. And we find that the model parameters could predict also where clinical and behavioral measures have chance performance, the computational model parameters could predict which patient with schizophrenia would benefit from a metacognitive training component added to their cognitive behavioral therapy. So this was also very promising in that by using this very simple gamified task that takes 5 minutes to administer, we could potentially improve treatment triage in individual patients. Similarly, the higher kind of outlook of this work is to integrate this into mobile digital frameworks such that we could do the model estimation in real time. So after participants play the games, they would get a display of their performance, but also their parameter estimates. And this is an ongoing study at CAMH where we integrate this approach in the context of the Toronto Adolescent Youth Cohort Study, where help-seeking youth are assessed every 6 months with various measures to look at biomarkers, cognitive markers, clinical markers. And we recently obtained CIHR funding to essentially integrate this gamified approach and be able to track psychosis spectrum risk trajectories over time. And with that, I would like to thank you very much for your attention and take any questions that you might have. Do you have any questions?
Thank you very much. So with this computational modeling of things that are happening in the brain, you can always add more, right? You can add like a memory component or an attention component or some internal, external priors, something like that. How do you cut off your models? Do you have like, is this some hypothesis you have or some measure?
Yes, that's a very good question. So the modeling framework is based on kind of first principles. So what is, so kind of stemming from, reinforcement learning and, a learning rate prediction error, Q learning. And so it essentially proposes a mechanism for a dynamic learning rate. So dynamic learning rate means that changes as a function of context, and that is modulated by other parameters. But this sort of kind of idea of a Kalman filter or Gaussian filter, the assumption is that this filter could go ad infinitum. So you could have context upon context. You can talk about the volatility of the context and so forth. So I think we keep it relatively simple. So it's essentially just a extended version of the Kalman filter, so where you have just another level on top of that, like a volatile Kalman filter, if you will. But in terms of memory or forgetfulness, the only thing that I guess you could change about the model is to add an autoregressive process. So the assumption is that instead of uncertainty kind of growing over time in the absence of input, you have a state that evolves as a Gaussian random walk and changes not only as a function of precision-weighted prediction errors, but there's also a drift on top of that. So that in the absence of input, you just drift towards your prior with some over time. But this is still kind of first principles. It's just really casting kind of forgetfulness and memory. You can think of it as, you know, the drift could be positive or negative, not necessarily towards the prior, but maybe you're drifting towards a certain bias, a certain attractor. And that in itself is like a bias term that you can introduce in your model. But I think it's still based on first principles because it doesn't have any additional assumptions. So it's not kind of putting in parameters. Having said that, of course, the cognitive tasks are very different. So sometimes you have to make binary decisions. Sometimes you have to make decisions under time pressure. So response time is very relevant. Sometimes you have to wager points. Sometimes you integrate, let's say, eye tracking or galvanic skin conductance. So the response model, so how you map beliefs onto choices, that can change. And that is very important as well, how you formalize that kind of forward model. And you know, how you capture behavior in very specific contexts and with very specific tasks.
Do we have any other questions for Dr. Diaconescu today? Yeah.
Question. This was a great talk, and thank you very much. Quite thoughtful in terms of symptom explanation. I really enjoyed it. I have like a high-level question, trying to really understand the construct overlap between neuropsychological terms and some of the terms we use in computational psychiatry. For example, all the prediction error, the volatility precision, mechanistically we speak about NMDA, receptors, playing a role. You think of neuropsychology in general, we talk about working memory as a framework that explains memories, or the NMDA problems underlies working memory deficits. What is the overlap concept-wise between something like working memory, which seems to underlie new processes, and how we construct the ideas around it?
Yeah, so of course, I mean, working memory is really about, I mean, there is a learning component there as well, because, for example, we're using kind of go, no go tasks where you have to learn stimulus action associations that are quite complex. So when should you act versus when you should inhibit an action? So that requires a great deal of working memory. So when you experience volatility or a switch in individuals with poor working memory function, then they will show a deficit in volatility learning just because you have all of these items that you have to hold at the same time. So I think there's a parallel there, and I think those things have to be distinguished well in experimental design. So you have to take into account that under high levels of working memory, you might see what you might deem as impaired volatility inference is really due to working memory load. And so that has to be certainly taken into account, but I think computationally, working memory would have an impact on the sensory precision of the prediction error. So when there's overload, working memory overload, then those prediction errors, those events will have a smaller impact on one's next predictions, just because they reduce the precision of the sensory input that we experience. But yeah, disentangling that from learning is very important.
Also, just wanted to say that today's talk has been recorded and it'll be on YouTube. If you have any further questions, you can send us an email and we can connect you with Andreea. So. No questions on Zoom, so please join me in thanking Andreea, and thank you all for being here today.